Hello, my name is Diego Perez Lebana and I am with the Game AI group at University of London. I'm presenting here RollingHorizon NeuroEvolution for general video game playing, a paper accepted for publication at the IEEE Conference on Games 2020. In this presentation, we're going to first see a quick summary of what are we doing and why. Then we'll describe the different methods that are involved in the study, the experimental work that we have done, and finally some takeaway messages. So, first of all, what can you find in the paper? What we are proposing here is a new statistical forward-planning algorithm, which we call RollingHorizon NeuroEvolution of augmented topologies. Because this is too long, we are just going to refer to this as rhNEAT. We are testing these methods in 20 games of the general video game AI framework. We will be testing different variants of rhNEAT, and also we will compare its performance with other main SFP algorithms, namely Monte Carlo Tree Search, or MCTS, and RollingHorizon Evolutionary Algorithms, or rhEA. We will also compare its performance against state-of-the-art results obtained by RollingHorizon variants in GVGAI. Results generally show that rhNEAT is inferior on average in performance to other SFP algorithms, although it achieves new state-of-the-art results in a few games. So, why are we doing this? Our main objective is to explore alternative representations for RollingHorizon Evolution. While RollingHorizon explores sequences of actions, each gene in the genome is an action in a sequence. What we want to explore here is using genomes to represent policies that can be used by the agent. rhNEAT is an example of these policies. So we want to study this from a general video game playing perspective, because we are essentially aiming for generality. We want to study if this algorithm can be applied to multiple games and not only to one of them. Because we are going to be using neural networks, we are going to face the problem of providing inputs to them. In this case, they will be features of the game state, and how these features are selected might impact importantly the final performance of the algorithm. In this work, we use statistical forward planning. These methods are AI playing algorithms that use a forward model. A forward model is a construction that, given a current game state as t and an action A, can generate one possible future state as t plus 1. Examples of SFP methods are, as mentioned before, Monte Carlo algorithms, which also include MCTS, and RollingHorizon variants. rhNEAT is an example of the latter group. Here we describe RollingHorizon evolutionary algorithms. The algorithm uses a population of individuals, and each one of them represents a sequence of actions that could be executed in the game. The individuals are subject to a regular EA operators such as crossover, mutation, and elitism. On each generation, new individuals are created. To do this, we select parents to create a new genome and apply, for instance, the crossover operator. If we are using uniform crossover, then genes will be taken uniformly at random from each parent until a new individual has been created. For mutation, we may pick one action at random and change it for a new value. In order to evaluate an individual, we take all the actions in the sequence, starting with the first one, and pass them through the forward model to advance the game step further. This process continues until the end of the game is reached, or all the actions have been applied. The final game state is evaluated using a heuristic or a value function that determines how good this state is. This value is then used as a fitness for the individual. This allows us to rank all new individuals and, using elitism to keep the best individuals, progress to the next generation. Once the decision budget is exhausted, RollingHorizon returns the first action of the best individual, which is then executed in the game. NeuroEvolution of augmented topologies is the other component we need in order to define rhNEAT. NEAT is a very known algorithm for evolving weights and topologies for neural network. Essentially, evolution is in this case replacing the role of backpropagation and gradient descent for training neural networks. There are many works on NeuroEvolution, so I would recommend consulting the original work by Stanley and Mikulainen or recent surveys published in the topic. It's important for this study to mention speciation, which is a variant that groups individuals into species. The objective is that only members of the same species compete. Species are formed by clustering individuals together according to a parameterized distance function delta, which is also defined in the paper. Now it's time to define our algorithm, RollingHorizon NEAT. rhNEAT has a population of P individuals. These individuals determine the weights, nodes, and parameters for the neural network. The initial networks that are created at the beginning of the algorithm are as simple as possible. They only have the input and the output nodes. For the input, we provide features of the current game state. For the output, we will have the action that the network recommends to be applied at that state. The size of the output then depends on the number of actions available on each game. The population is evolved using regular EA operators, such as crossover, mutation, and elitism. The interesting aspect is how is each individual evaluated. The key is that we use what we call a RollingHorizon NEAT rollout. First, we take an individual and use its genome to form a neural network. The inputs are extracted from features of a given game state, and then they are fed to the neural network to obtain the output. This is the action to execute. Then we roll forward the state, using the forward model with the action provided by the network. We repeat this process until we reach a rollout depth L, or the end of the game. Once we reach the end of the rollout, the final state is evaluated to assign a fitness to this individual. When the thinking time is over, our recommendation policy determines that the action that is generated by the best individual, this is, by the best neural network, will be executed in the game. This slide illustrates how highly parameterized rhNEAT is. In this table, we can see how many parameters can be tuned to adjust the behavior of the algorithm. All these parameters are also defined in the paper. We are going to illustrate now more clearly what the differences between vanilla RollingHorizon and rhNEAT are. What you can see here is the default RollingHorizon algorithm, a population of action sequences on the left and new individuals created by applying evolutionary operators. The evaluation of the individual consists of the execution of each one of the actions in the sequence, one by one, until reaching the state Sn. This state is then evaluated to provide a fitness to the new individual. In rhNEAT, the first difference is that the individuals in the population no longer represent sequence of actions, but a series of weights, connections, and parameters for neural networks. Evolutionary operators are applied the same, but rather than directly evaluating the genome of the individual, we use this to generate a neural network. Now the actions for rolling the state forward are the outputs of the network at that state, which inputs are features of the current game state. We repeat this process during L steps, reaching now the state that needs to be evaluated as in RollingHorizon. Note that, in this case, the length of the rollout is independent from the length of the individual. As mentioned before, we use the GVGAI framework for the experimental work in this paper. The GVGAI framework is a benchmark that allows running AI agents in a series of 2D arcade games. These are games where an agent must return an action in real time, and the framework has more than 100 games implemented. The objective of the framework is to promote research in general video game playing, and several competitions have been run in previous years to this end. Given the large number of games in this framework, we have used previous studies that provide different classifications for them. The work by Mark Nelson ranks games depending on the performance of MCTS agents in them. The other work by Philip Bontrager et al. Classifies games by types attending to the performance of different agents. We have selected a balanced set of 10 stochastic and 10 deterministic games, uniformly selected from the classifications of these studies. Here are some examples of the games included in the final set. This set has also been used in previous studies in GVGAI, which allows us to compare our results with theirs. The GVGAI framework proposes a common API for agents to play in these games. Apart from providing a forward model, GVGAI provides information about the current game state. This information includes characteristics like sprite types, categories, and positions in a grid-based structure. For this study, we have taken the following features from the game state, which will be used as inputs for the neural networks employed by rhNEAT. The position in X and Y coordinates of the player or avatar normalized. The orientation of the avatar also normalized. The health points of the avatar between 0 and the maximum health points possible. Avatars can pick up resources in certain games. In this work, we capture the amount of a maximum of 3 resources picked up, from 0 to a maximum of 20 units. Finally, For each type of sprite in the game, we capture the distance and orientation to the closest sprite of the given type. These are NPCs, immovable and movable sprites, resources, portals, and other sprites created by the avatar. Moving forward, we present here our experimental setup. All experiments are executed in the 20 GVGAI games selected, running 100 repetitions per game. Each game has 5 levels, so we run 20 repetitions per level. The population size of RollingHorizon and rhNEAT is 10. The rhNEAT rollout length, as well as the RollingHorizon individual length and the MCTS depth, is set to 15. We also have fixed the thinking budget for an algorithm to 1000 users. This is, each algorithm can use the next function of the forward model 1000 times per action decision. This limit respects on average the constraints of real time, while allowing us to replicate the results in different hardware architectures in a fair manner. Finally, we define the following value function to evaluate fitness of the states. This is a general function that is adequate for many games. It assigns the value of the score if the game is not finished, a high positive number if the game has been won by the player, and a high negative number if the game was lost. In the first set of experiments, we analyze the impact of different components of rhNEAT. One of them is speciation, which we have already mentioned before, so we try variants of the algorithm with and without this component. The other component, which we call population carrying, consists of carrying or discarding the entire population in rhNEAT after each game frame. On one hand, carrying population allows rhNEAT to not having to learn again new parameters for the neural network. On the other hand, it might be slow to adapt the individual to radical changes in the dynamics of the games between different frames. The table displayed here shows the results of this test. The winning rate indicates the proportion of games won with the standard error of the measure. The third column indicates in how many games the raw algorithm achieves the highest positive win rate. The value indicated between parentheses indicates in how many games this algorithm is strictly better than the other three. Finally, the last column indicates in how many games the raw algorithm achieves the highest score in the comparison. These results suggest that these two components make the baseline rhNEAT stronger, while showing the population carrying is even more crucial to the performance of the method. This is equivalent to keeping the tree in MCTS or applying a sieve buffer in RollingHorizon, so this result is not completely surprising. We can also see the results per game, and the general trend is maintained, with rhNEAT carrying the population and using speciation being better than the other variants in most games. It's interesting to see, like in most GVGAI studies, that this rule of thumb doesn't apply to the 100% of the games, although in this case it's very consistent. It is also interesting to appreciate that games can also be grouped in different clusters, attending to the general performance of the method. This is a testimony towards, among other things, the nature of the games and the adequacy of the feature selected to a subset of them. There is a subgroup of games where the winning rates are above 80%, some intermediate games with rates about 20%, and a subgroup with very sparse victories, and a final set of games where no agent is able to achieve a single victory. The following two experimental studies explore different ways of assigning fitness to rhNEAT individuals. This one attempts alternative computations of the fitness based on the reward observed on each state during the rollout. rhNEAT uses the reward of the state at the end of the rollout to assign value to the individual fitness. This is equivalent to the way we described the algorithm in a few slides ago. One alternative is to accumulate the rewards of all these states visited during the rollout. This is what we call the rhNEAT ACC here. Another option, ACC disk, is to also accumulate rewards, but discounting the rewards with a discount factor in the classical reinforcement learning way. We have set this value to 0.9. The results of these experiments are very similar for the three versions. We think that this may be due to the smoothness of the reward landscape, presenting similar rewards in short and long-term horizons. There is, however, a higher count of games, 12, where the default rhNEAT achieves the highest average score. So we'll proceed with this version for the following experiment. This third experimental set explores how can we update the fitness of an individual through several generations of the algorithm. Because of the stochastic nature of the games, and therefore their rollouts, individuals are evaluated more than once through the generations of the algorithm. We propose three variants here. The default one, rhNEAT, overrides the fitness of the individual with the last evaluation performed. This allows the algorithm to quickly adapt to changes in the environment, although it might make individuals more volatile to likely or unlucky rollouts. The other two options consist of computing averages of different fitness obtained for the same individual. One possibility is to obtain the arithmetic average of all evaluations, while the other is to establish a learning rate, which is set to 0.2 here, that updates the individual fitness with each evaluation. Results show a similar performance of the default version and the learning rate one, with the option that uses the arithmetic averages slightly below win rates. Because of the high number of games with the highest win rate corresponds to rhNEAT, we'll continue with this algorithm for the final experiment. It is, however, interesting to observe how close the results are, and it's possible that different or dynamic learning rates can still yield good performance in this case. The final experiment compares rhNEAT with other SFP methods, and andintroduces and RollingHorizon, and also shows the state-of-the-art results of RollingHorizon methods in GVGAI. It's important to highlight that these state-of-the-art results do not correspond to a single algorithm with the same parameters. Instead, it represents the hypothetical best performance that can be achieved by selecting the best parameters on each game. In any case, it is clear that rhNEAT is still far from the performance of other SFP methods. It is, however, interesting to see how rhNEAT is able to achieve the highest positive win rate in 2 games, surpassing the state-of-the-art. Results in this plot show the comparison of these algorithms and the state-of-the-art in all games separately. rhNEAT achieves comparable results in the set of games where the other algorithms achieves close to 100% victory, so it's good to see that for these games rhNEAT does not fall below expectations. The middle group shows, however, worse performance of rhNEAT in a couple of games, although the 2 new records can be observed in games where other methods perform very poorly, Camel Race and Crossfire. It is also significant the poor performance of rhNEAT in the game Chopper compared to the other SFP methods. In general, we observe different performance in different games, as usual in these studies. We believe that it is the selected features of the game state, the ones that impact the performance of rhNEAT. For instance, it seems obvious that the neural network is able to learn that individuals who minimize the distance to the closest goal in the camel race game are more likely to achieve victory. In Chopper, however, a game that has many sprites in play, it's possible that rhNEAT's short-sightedness of only considering the closest sprite of each type is hindering the algorithm. Just to finalize now, our objective with this work was to explore different representations for RollingHorizon Evolution by presenting a new framework in which this can be done. Results for this particular algorithm are not better on average than other methods, but it still achieves a new win rate record in some of them. We believe that the performance of rhNEAT is highly dependent on which game state features are selected and also possibly on the high parameter space of the algorithm. Therefore, we suggest exploring these spaces to keep improving on this method. Possible avenues for future work include the adaptation of other EA enhancements like controls to keep diversity within the population and possibly multi-objective approaches to help with feature selection. Current work in CNNs can also inspire the use of convolutional layers to automatically extract game features, although how to overcome the computational cost of these in real-time games is still not clear. Finally, in line with the motivation of this paper, there might be other interesting representations that work with this RollingHorizon framework. For instance, individuals could encode other types of policies, such as those derived from genetic programming. Examples are grammatical evolution or tangled program graphs, which have some previously good results in general video game playing. Thank you all for watching this video, and if you have any questions, do not hesitate to contact me at my email address shown in this slide. Bye.